So, brand new topic for us to have a look at this half term. It's C5, which is all about chemical changes. So there's quite a lot of chemical reactions to look at here. Don't worry that we're not actually going to be able to do them outside of the lab, but we will obviously come back to them when we're back in the school setting. So the first part of this topic is actually something you've done before, so it's quite a nice place to start. You've done it in year 8. It's called the Reactivity series and Displacement reactions. So here I've got the Reactivity series of metals: potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. That is one reactivity series of metals. There are some others out there which include other elements such as lithium and strontium and things like that. But these are the basic ones you need to be aware of. And unfortunately, you used to be able to get this in a GCSE exam. Now you have to memorize it. So you need to remember all of these in order. You can create your own sort of mnemonic or song or poem to go with it. So I think the one that I've shared with you said, "Please stop calling me a careless zebra. Instead, try learning how copper saves gold." Got there in the end. So again, you could create your own one, or you, like you say, just have to learn this order. But again, we'll come across it now in year 9. You'll come across it again in a separate topic in year 10 and again in year 11. So you will get used to actually coming across this reactivity series. There's one more that we're going to use today, which I'm just going to slot in here, which is lithium. And hopefully you remember from our last topic before half term that does make sense, because the alkali metals are at the top. They're the really reactive metals, and then the sort of transition metals are towards the middle and the bottom. And you'll notice that in the reactivity series of metals, that's particularly the one that I've drawn, there are 2 things which are in green and not purple. One is carbon and one is hydrogen. So why have I put those as a different colour? Well, the super observant out there will notice that it is the reactivity series of metals, and these 2 things, carbon and hydrogen, are non-metals. So why do we include them on the reactivity series, I hear you ask? Well, they are both very, very good at extracting other metals, or extracting more particularly less reactive metals. So I could use carbon to extract zinc, iron, tin, lead. I could use hydrogen to extract copper and other metals as well. So we keep them on there because we can actually use them as non-metals to extract others. How would we extract them? We'd use something called displacement reactions, which we'll come on to in a moment. So this is the reactivity series. How was it arrived at though? How did we know that the order of reactivity goes from potassium down to gold? Well, how do we find out anything in chemistry? We do chemistry, we do chemical reactions. So we could have done an experiment like this, where we placed each of these metals, all right, into different test tubes of acid, and they would have reacted to form hydrogen gas, and we could collect or we can measure the volume of gas produced every 10 seconds. So that's one way we could go about doing it. Obviously, if we were going to do that, we'd have to keep certain things the same, certain control variables. So in this experiment here, all right, what would you think I would need to keep the same to enable me to get the correct results? All right, just have a think about it. Type some answers into the chat as well, and I'll come back to it. So what would I need to keep the same in this experiment that would enable my results to be reproducible, i.e. valid? Someone else could go and do the experiment and get similar results. So what are my control variables? So the same beaker, first answer we've got. So the same size beaker, absolutely, yeah, that will make a difference. So the same size test tube in this particular case could make a difference. The same volume of acid is a very important one, so I'm going to put that one down. So the volume of acid, so that's how deep the acid is in this test tube. If I use that much acid for zinc, but then I use this much acid for lead, it's not going to give me valid results. Okay, so yeah, we've got the same volume of the acid. Anything about the metal that you think we need to keep the same? Yeah, well, again, some people are saying the amount, which is not a great word we like to use. So again, it's a good time for us to actually revise this. Whenever we're talking about liquids, we talk about volume. Whenever we're talking about solids, we use the word mass. Okay, so the word amount is not really accepted anymore. So it's the mass of metal. So what we could do, great idea that is we take all these metals and just weigh them in some scales to make sure we've got the same mass each time. So we've got volume of acid, mass of metal. Someone said same temperature. Yes, of course. So the same, doing it at room temperature because that will affect how quickly the reaction happens. Very good answer to that. All right. Another thing as well. What else could we say about the acid? I'm going to say concentration. So the concentration of acid is going to be crucial. And concentration is just, I don't want to use the word strength, but you see it on squash bottles all the time, don't you? Double concentrate, which means it's twice as strong in your eyes. It just means there's twice as much orange squash in the same volume. So concentration of acid, it could be 1 mole per decimeter cube, 2 mole per decimeter cube. Keeping that the same is going to be crucial, along with temperature and all those wonderful things. And that's how the reactivities arrived at. And like I say, these results are reproducible. They've done experiments like this, for the last 100 years to arrive at this reactivity series. So again, you need to be aware of this. So I'm going to keep it on the board, and we're going to start looking now at displacement reactions. Okay. So, what is a displacement reaction? Well, we looked at this with the halogens, where we said that a more reactive halogen will replace a less reactive halogen from one of its compounds. And it's exactly the same for metals, all right? A more reactive metal will replace a less reactive metal from one of its compounds. Okay, so I've used the word displace there. Displace, replace, fairly interchangeable. You can use either or. So what does that mean? Well, what I'll do is I'm going to use a couple of examples from the worksheet that I've set. So on the worksheet that I've set you this week, there's several different levels. There's like level 2 answers up to level 2 questions up to level 8 and 9 questions. I'll do a couple of examples from each to help you out. So the first one, if we just have a look at this, is whether or not we think these reactions will happen. So let's have a look. So we've got copper plus zinc sulfate will make copper sulfate plus zinc. And these are sort of the level, I think it's level 2, level 2 questions. So I'm basically asking you to predict whether you think that reaction would take place, all right? So just by saying whether or not you think it'll happen, we'll probably, it's probably level 2. To extend it further, try to explain why. So will that reaction happen, yes or no? So what do we think? Type in some answers. Already got a great answer there. It would stay the same surely because zinc is more reactive. Correct. Basically, the sulfate ion has a decision to make. The sulfate ion could stay with zinc or go off with copper. And you've got to look at the reactivity series here. It will stay with the most reactive one. So if we have a look, zinc is there and copper is there. So will the sulfate ion stay with the zinc or will it go off with the copper? Well, because zinc is more reactive than copper, there will be no reaction. So what I'm going to do is I'm just going to write a cross there. No reaction. Okay. We'll have a go at one more from that particular one. So we'll say iron plus gold nitrate makes iron nitrate plus gold. Okay, so have a look at that and come up with an answer as to whether or not you think that reaction would happen. So what do we think? that reaction happen? Iron plus gold nitrate makes iron nitrate plus gold. Well, let's have a look. How should we go about answering this? So it's the nitrate has to make a decision. It's either going to stay with gold or iron. Well, gold is there. Iron is there. So iron is more reactive. So the more reactive metal is going to replace the less reactive metal. So all that happens here is it's a bit like swapping partners, is that the iron will take the nitrate to make iron nitrate, and you're left with gold at the end. All right. So again, they're the fairly standard questions. Right? If you ever ask to answer in a bit more detail as to why that reaction happens, don't just say iron is more reactive. Finish the sentence. Iron is more reactive than gold. So always compare the two metals in the question. All right. Okay, then let's move forward and look at some level 4 questions then. All right, so these will get more difficult. This is a fill in the gaps one. So we'll do level 4, we'll do question 1 and question 2. So we've got magnesium plus silver nitrate. And you've got a gap plus silver. Okay. And then you've got aluminium plus blank will make aluminium sulfate and copper. So what I'm going to do is I'm going to leave that there, and these reactions do happen. I want you guys to work out what goes in the two gaps. So have a go and type in some answers for me. Okay, let's have a look at that first question then. So I told you these reactions do happen, but let's try and prove that by looking at the reactivity series. So magnesium plus silver nitrate. Is magnesium reactive enough to displace the silver from silver nitrate? So magnesium is there and silver is there. So magnesium is definitely reactive enough. So what you get is magnesium nitrate and silver. So again, that will steal the nitrate from silver nitrate, and you end up with silver being produced. All right. The next one then, it's probably a little bit more tricky, this one. So what goes in this gap here? Aluminium plus blank makes aluminium sulfate plus copper. So the aluminium is reacting with something to produce aluminium sulfate and copper. Well, whatever's the conservation of mass, right? Whatever's on the left of an equation must be on the right. And even though you can't see the symbols, you can see the names. So on the left-hand side, I've got aluminium. On the right-hand side, I've got aluminium. But what I haven't got is copper or sulfate. So what goes in this gap here is copper sulfate. All right. And again, hopefully you can use those two examples to have a go at the other two, which are in the level 4 questions. Okay. So let's have a look at. So let's look at level 5 then. Okay, so level 5 questions. So what have we got here? We've got zinc and copper sulfate. And then we've got, let's choose a different one. Let's choose question 4, gold and copper sulfate. Okay, have a go at filling in, all right, the rest of those 2 equations. If you don't think a reaction is going to happen, just write the words no reaction. What have we got to say then? There is a reaction for the first one, someone said. Yep, absolutely spot on. If you do think there's going to be a reaction, try and think why. That's a perfect answer. Really well done. So the first one, zinc plus copper sulfate. Someone says that we do get a reaction, so we get zinc, sulfate, and copper. And then Simran's very accurately said, why do we get a reaction? Because the zinc is more reactive than copper. All right, and I'll just prove that. Zinc is there. Copper is there. So is zinc reactive enough to replace the copper in copper sulfate? So is it reactive enough to take the sulfate away? The answer is yes. So we end up with zinc, sulfate, and copper. Now, the last one. All right, we've got an answer. Yep, well done, Ashton. There is no reaction for this last one. No reaction. And why is there no reaction? Because gold is not reactive enough, or gold is less reactive than copper. Does gold have the reactivity to take the sulfate away from copper? Well, where is copper? Copper is there. Gold is there. So the sulfate is going to stay put. It's going to stay with the copper and not go off with the gold. So you get no reaction with that one. Okay, right. We'll move on to the level 6 and 7 questions now, and we'll do a few of these because they're symbol equations. Right. So, okie dokie. So what have we got? Let's do the first one, Na2. So I've got symbols now, and thankfully you don't need a periodic table for this because I've got the symbols next to the various different metals here. So could you, all right, complete that equation if you think it is going to happen, and if it does, what will it look like? And then have a go at the one afterwards as well. If you don't think these happen, just write the words no reaction. So will these reactions happen? And if they do, complete the equations and make sure they're balanced. All right. So I'll give you a couple of minutes to have a go at this. put displacement twice. So what is going to reduce? Right. A couple of people have said that the first one, we get no reaction. And that is absolutely correct. First thing I would do, and I'm guessing they did that because they identified the metal first. They knew that was copper or calcium, if you think my handwriting is that bad. And this Na is sodium. So it's a battle between sodium and copper. Is copper reactive enough, okay, to take away the rest of this, right? And it isn't. So because sodium is towards the top of the reactivity series, copper is down here. So can the copper take away this SO4? No, it can't. I'm just going to finish this equation actually. I'll just tell you how would you work out what this thing is called? Sodium what? What is the rest of the name of this particular compound? Well, it's got sulfur in it, which is S, and it's got oxygen. So it's sodium sulf. Now, there's two ways we can finish this. It's either sulfate or sulfide. And the difference is, if it was just sulfur on its own, it would be sulfide. If there was oxygen with the sulfur, it becomes sulfate. Yeah, and that's true for any sort of non-metal ion. So this one, for example, at the bottom, has got nitrogen in it. Now, if it was just nitrogen on its own, it would be nitride. If it's got oxygen with it, it'd be nitrate. All right. Same with phosphate. So you could have phosphide if it was just phosphorus on its own. You could have phosphate if there's oxygen with it. Okay. So let's try and work out what this bottom one is. It's Ag, which is silver, and it's NO3. So it's definitely got nitrogen. So it's nitr. But is it nitride or nitrate? Well, because it's got the oxygen in it as well, it's nitrate. And potassium. So the question is potassium reactive enough to replace the silver? Right. So potassium is up here at the very top of the reactivity series, which means it's more reactive than all the other metals. So it should be a fairly straightforward one, this, but let's just make sure. And silver is towards the bottom. So you end up with potassium nitrate and silver. Okay, but again, we need to do the symbol equations. Now, with these questions, it's quite nice because it is just a simple swap job. All right, so just swap the K for the Ag. So KNO3 plus Ag. And the reason why we can do that is because the charge on a silver ion is +1, and the charge on a potassium ion is also +1. It becomes a bit more complicated when we get to the level 8-9 questions in a moment. All right. So again, that's how you have a go at the rest of those questions. If you think there's not going to be a reaction, just write no reaction. And then obviously if you think there is, have a go at writing a symbol equation. All right. So let's have a look at the final set. So again, we're looking at level 8 and 9 questions now, where you'd have to create your own equations from scratch and then balance them. So we are really looking at the the higher level stuff now. And this is something that if you don't get it in year 9, you're in the 99.999% of chemists who don't get it because you haven't had as much practice at it. So don't worry about it. But I'm introducing it now so you have a bit more practice. So we're going to look at a level 8 or 9 one. So, and we've got magnesium iodide plus potassium. Well, the first thing to do here, all right, is to find out whether or not you're actually going to get a reaction. So I need to find, what are my metals here? I've got potassium, which is at the top, and I've got magnesium, which is just here. So potassium is more reactive than magnesium. So I am going to get a reaction here. So what I'd probably do is I'd probably just write the word equation first, just so I know. So I know that the potassium is going to take the iodide away. And I've got magnesium. Okay. So I now need to, underneath each of these chemicals, write down what the formulas of them are. Well, I don't know the formula of magnesium. I'm going to have to work that out, okay? But I do know that potassium is K. I don't know potassium iodide, and I do know that magnesium is Mg. So you need to work out what the formula of magnesium iodide is going to be. And that's where that table of ions is going to help you. So it tells you that, well, reading the name, magnesium iodide suggests that it's got magnesium ions and iodide ions. So I need to know the charge of both of those. Now, in the worksheet I've given you, you've got a table of ions and charges. You won't have that in the exam, but you'll get used to the common ions and you'll be able to work out a lot of them from the periodic table. So I know magnesium is in group 2. So when it's reacted and formed a compound like this, it will have a 2+ charge. So it's magnesium 2+. So I'm just going to work out what the formula of magnesium iodide is just here. Iodide, well, according to that table, it says that iodide is I1-. Okay. How would you know that it was 1- without that table of data? All right. Well, you look at the periodic table, you find iodine. Iodine is in group 7, which means it's got 7 electrons in its outer shell. So when it has reacted, it will form iodide by gaining 1 electron. If it gains an electron, it becomes negatively charged. So how am I going to turn these into a formula? Because the charges, the positives and the negatives, need to cancel out. A compound has no overall charge. The number of protons, the number of electrons is balanced. But here, look, right, these need to be balanced. So how would you do it? Well, I've got 2 positive and I've got a 1 negative. So I'm going to need another negative, all right? Just by having a look, imagine it's like a seesaw, if you like. Have I got the correct number of negatives and the correct number of positives? So I've got a 2+ on the left, and I've got 2 minuses on the right. So the formula is Mg, and how many of them have I got? 1 of them. I2. Okay. So you've got to make sure they're balanced, all right? Yeah, someone just asked that iodine is a diatomic molecule. Good, it is a diatomic molecule, but we're not dealing with iodine, we're dealing with iodide, which is an ion. It's an iodine atom which has gained an electron. Good point. So having a look at this, I mean, you could work it out this way. I could teach, well, I have done this with you before, or you could do the crisscross way. So what is the crisscross way? Well, I'm going to go back to what we know. So we know that magnesium is a 2+ ion and iodide is a 1- ion. And all you need to do, really, is just swap the numbers over. So whatever number is there goes there. And then whatever number is there, which is a 1, goes there. So it ends up being Mg1I2, which is what we worked out using the other method as well. So I'm going to write that as my answer in here. So it's Mg1I2. 2. Okay, and there's one more formula I need to work out, which is potassium iodide. So using that grid, it tells me that a potassium ion is 1 plus and iodide is 1 minus. Well, this is a nice straightforward one because +1, -1, balanced in a 1-to-1 ratio. So I don't have to do any crisscrossing or anything like that. I can just simply put Ki. It's a nice 1-to-1 ratio. So I've got all of the chemical formulae correct. I now need to see is this thing balanced. Right, so more balancing equation practice. Well, what have I got on the left? I've got 1 Mg, I've got 2 I's, and I've got 1 K. On the left-hand side, I've got 1 K, I've got 1 I, and I've got 1 Mg. So compare and contrast. Have I got the same number of atoms on the left as I do on the right? The answer is no, I don't. I need to get another iodine on the left. So as someone's already alluded to, which is brilliant, I need 2 lots of that. Because by doubling all of that, I go from having 1 iodine to 2. But it doesn't just double. By putting the big number 2 there, it doesn't just double the number of I's, it will also double the K's. So just stand back. Are the numbers on the left the same as the numbers on the right? Well, Mg, Mg, good. So they're balanced. 2 I's, 2 I's. 2 K's, 1 K. So what do I need to put on this side? I need to get another K onto this side somehow, and someone's already pointed it out. 2. So again, these are the really tough questions. If you can't do them, then like I say, do not worry about it. You will do by the end of year 11. All right. Let's have a go at one more then. Let's have a go at one more together, and I'll leave you get on with the rest. So let's go with lead sulfate and zinc. So in fact, no, let's choose a different one. Let's choose a more complicated one. Yeah, iron 3 nitrate and aluminium. Let's try that. So this is question 3 in your level 8 to 9 work. Okay. So, am I going to get a reaction, yes or no? Well, hopefully you can all see by now that you will get a reaction. All right. So, because aluminium is up here on the reactivity series and iron is there. So they're fairly close, but the aluminium is more reactive. So the aluminium is going to take the nitrate away to make aluminium nitrate and leave iron. So it was a bit squished up there. I'll spread it out down here. So again, I need to get all my chemical species right. So I know there's going to be a reaction, and I need to get everything in place. So I know that iron is Fe. I know that aluminium is Al. So I need to work out what this thing's formula is. So first thing I'm going to bring your attention to is it says iron 3. So this is actually a Roman numeral 3. And the Roman numeral tells you what the charge on the iron ion is. You'll notice in your table, you've got Fe2 plus, and you've also got Fe3 plus. And that's because, going back to our last topic, we discovered that transition metals can form different charged ions. So they can form 2 plus ions by losing 2 electrons. They can form 3 plus ions by losing 3 electrons. All right. So the 3 lets you know which one you're dealing with. So it's iron 3. So it must be the 3 plus ion I'm dealing with. And then the nitrate ion is NO3 1 minus. Okay. So I think in your table, it will just say minus, but I'm going to put the 1 there because I'm going to need that. All right. Now, is that balanced? Do they balance as a 1-to-1 ratio? If I had one of those, I'd have 3 pluses. If I had one of these, I'd have just 1 minus. I need another couple of those. So I'm going to do the crisscross method here. All right. So I'm going to write down FeNO3. I know that iron 3 nitrate contains iron and nitrate. So it's got Fe, it's got NO3. But what ratio? Well, let's do the crisscross. That number 1, which is on the NO3, will go down there. All right. And then this number 3 will go down there. But here we've got to be careful, because what I've done is by putting that 3 next to the NO3, it looks like NO33. So what I need is to put brackets around it. Okay, so I put brackets around it to sort of protect it. So now it's FeNO3 3 as opposed to being FeNO33. So the brackets are important. So again, that's all sorted. I can sort that one out now. So that's FeNO3 3. All right. And now we've got to do aluminium nitrate. So we'll do the aluminium nitrate working out down here. So according to that table, aluminium, well, it's in group 3. So when it's reacted, it is a 3+ ion. And I've got nitrate again. Okay. So what would the formula of aluminium nitrate be? Try and work it out and try and post an answer. What's the ratio of aluminium to nitrate going to be? You might want to set up your crisscross. Good practice is to just put that in brackets anyway to stop you making a mistake, because even if you don't need the bracket, you won't get penalised for having it. Swap the numbers over. Do the crisscross method. And we've got, yep, well done. So that number, which is a 1, ignore the minus, goes there. And that number, which is a 3, goes there. We end up with Al brackets NO3 3. All right. Now, we're still not finished yet because we need to make sure it's balanced. So this is, let's just write down what we've got on either side. So here we've got 1 Fe. Now in the bracket we've got 1 nitrogen. You see that? 1 capital N, 1 nitrogen. But because there's 3 lots of this bracket, there's 3 N's in total. And inside the bracket we've got 3 O's. And because there's 3 lots of that, what's 3 times 3? We've got 9 O's in total. And we've got 1 Al there. Go to the other side. We've still got 1 Al. We've got 1 Fe. We've got 3 N's. Well, we've got 1 inside the bracket, but we need to times it by the little number after the bracket. And we've got 9 O's. Okay. And if you stand back and admire, hopefully you can see that is actually already a balanced equation. But we're going to spend loads of time looking at constructing equations over the next 2 years. So again, don't worry about it at all. All right. And I hope basically you've had enough information there to be able to access the work I've set this week. And like I say, if you can't get to the level 8, 9, I wouldn't worry about it too much. It's just there to try and challenge you already. Level 8s and 9s are things you should be going